Picture this. You're sitting there, opening up your Cambridge IGCSE computer science paper. The clock is absolutely ticking down, right? The pressure is on. And boom, you see what looks like the easiest conversion question ever, a total freebie. But hold on, you're actually about to step right into a massive examiner trap.
Let's look at this classic question. Convert Denary 27 to hexadecimal. You wouldn't believe how many learners just instantly write down a 2 and a 7. I mean, honestly, it kind of feels logical, doesn't it? Just map the numbers straight across, easy.
Except it gets you exactly 0 marks. 0. Ouch. Falling for this direct conversion trap literally costs students vital grade boundaries every single year. So today, we're going to play Data Detective. We're going to crack this mystery wide open, figure out exactly why that shortcut is completely flawed, and get you the bulletproof framework to nail those top marks every single time.
Section 1. The suspects, base 10, base 2, and base 16.
So, let's identify the core number systems in our lineup for this explainer. On one side, we've got our standard Denary system. That's base 10. It uses digits 0 through 9 and, well, it's basically the numbers we humans use to count and calculate with every single day. On the flip side, we have the much broader hexadecimal system, base 16. This one uses 0 to 9 as well, but then it does something wild. It seamlessly switches into letters A through F to represent the values 10 up to 15. The big problem here? These two systems absolutely do not speak the same language. To get them talking, we have to use the ultimate computer language, binary. Good old base 2, made entirely of ones and zeros. But why ones and zeros? Well, underneath all the flashy software, your computer's processor is just billions of microscopic transistors. And these transistors? They're basically tiny switches. They either hold an electric charge, which is an on state, or a 1, or they hold no charge, which is an off state, or a 0. It's really that simple.
Let's see how that works in real life. Take the binary number 10011. If we use binary place values, which, remember, just double every time you move right to left, so 1, 2, 4, 8, and 16, we just add up the column headers wherever we see a 1. Okay, so we've got 116, no 8s, no 4s, 1, 2, and 1, 1. Add those together, 16 plus 2 plus 1, and boom, you get the Denary number 19. See? Not so scary?
Section 2. The clue, the 4-bit nibble framework. In just a minute, I'm going to show you the exact examiner wording that turns a basic 1-mark answer into a full 3-mark answer. But first, check this out. This is the ultimate cheat sheet that every data detective absolutely has to memorize. It maps Denary values 0 to 15 straight across to hexadecimal 0 to F, and crucially, it links both of them to a 4-bit binary code. So for example, Denary 10 is hex A, which is binary 1010. Lock this 4-bit structure into your brain because it is literally the key to unlocking this whole conversion process. Here is the golden rule. You cannot jump straight from Denary to hexadecimal. You just can't. You have to use these specific steps to safely cross the binary bridge. Step 1. Translate your starting Denary number into an 8-bit binary byte. Step 2. Take that 8-bit byte and chop it right down the middle into 2 4-bit chunks. Fun fact, computer scientists actually affectionately call these nibbles. Yeah, half a byte is a nibble. Anyway, step 3. You convert each of those individual nibbles into its single hexadecimal digit. Let's actually put this framework to the test with a real number. Let's use 95. Okay, step 1, convert 95 to 8-bit binary by finding the place values that add up to 95. That gets us 0101 1111. Step 2, chop it in half. Our first nibble is 0101, our second nibble is all ones. Step 3, we pull from our mental cheat sheet. 0101 is 5 in Denary, so that's a 5 in hex. And 1111, that's 15 in Denary, which translates to F in hex. Smash them together and Denary 95 securely becomes hexadecimal 5F. Nailed it. Section 3. The interrogation. Pause and solve.
It's time to up the stakes a bit. You have the framework, now let's see if you can apply those detective skills. Here's your mission. Convert the Denary number 205 into an 8-bit binary number, and then convert it into hexadecimal. I want you to pause this explainer right now, grab a piece of paper, and apply those 3 steps.
Just remember, getting that 8-bit binary sequence first is the only way you're going to dodge the traps. Map out your place values, starting from 128 all the way down to 1. Figure out exactly which ones add up to 205, write down your ones and zeros, and then perform that famous nibble split. No rush, take your time.
Okay, Let's review the evidence. To get 205, your 8-bit binary should have been 1100, 1101. Then we split that into our two nibbles, 1100 on the left and 1101 on the right. The first nibble is 12 in Denary, which gives us C in hex. The second nibble is 13 in Denary, which is D in hex. Put them side by side, and if you got CD, wow, you just successfully navigated the binary bridge. Seriously, fantastic work.
Section 4. The verdict. Mastering the mark scheme.
Because, getting it right on scratch paper isn't quite enough for exam day. Think back to that hook from the very beginning. We can totally see now exactly why directly converting Denary 27 to hex 2 and 7 is such a disaster. The actual mathematically sound top-band way to do it is converting 27 to the binary 0001, 1011. Splitting that gives us a left nibble of 0001, which is 1, and a right nibble of 1011, which is 11, or B. So the real answer is 1B. The nibble framework is bulletproof, direct mapping is just a complete illusion.
And this right here reveals a massive hidden trap embedded in the syllabus itself. When examiners use command words like calculate or show, just writing down the final hex value, even if it's 100% correct, will cost you dearly if you don't have the binary working out. The examiner wants to see your whole investigative process, not just your final verdict.
Basically, the rule of thumb is 1 mark requires 1 distinct technical point. So to grab all 3 marks for a conversion question, write down every single step of your investigation. Show that 8-bit binary sequence nicely and clearly for mark number 1. Visually demonstrate the 4-bit nibble split for mark 2, and then clearly state your final hexadecimal value for the 3rd mark. It is a ridiculously simple, highly effective formula for maximum points.
Section 5. Case closed. Or is it?
Okay, we've solved the mechanics, our framework is tested, and we know exactly how to secure the marks. But our data detective journey is definitely far from over. This leaves us with a huge open loop. What is the actual point of hexadecimal in real-world computer science? Like, if computers only fundamentally understand those microscopic ones and zeros, why on earth are we introducing letters and a base 16 system into the mix at all? Wouldn't it be vastly easier to just stick to binary?
To unlock full marks on the theory side of Paper 1, you have to grasp the practical, real-world applications of hex, because it's everywhere. You'll find it buried in your network MAC addresses, flashing in critical system error messages, and it even defines the very color codes you are looking at on your screens right now. Knowing how is honestly only half the battle. Knowing why is what truly separates the good students from the great ones.
By the way, if you found this structured approach helpful, then I've got great news. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE. We break down complex topics into clear, visual, step-by-step explainer guides just like this one.
So what do you say? Are you ready to crack the final code and discover the true power of hexadecimal? The next clue is waiting for you. Click on the next explainer right now. Let's close this case for good, master the real-world applications of hex, and completely secure your top grade. I'll see you over there.